Nick's now going to speak from more of an amateur's perspective on ground-based amateur observation. Nick, hand over to you.
Thanks, Jeremy. Can everyone hear me okay? No. No? Yeah. Good. Okay. So we've heard a lot today about some fantastic space missions, and when you look at the technology involved in those space missions and when you look at the results that they can achieve, you wonder whether there's actually any space left for us as amateurs in observing solar system objects. And I think there definitely is, and I'd like to convince you of that in the next 30 to 40 minutes. And there are a few really good examples of that that have happened recently that I'm going to go through. And, oh, haven't I turned it on? Blimey. Is that better? Yeah. Sorry. Okay, so I'm going to try and convince you in the next half an hour or so that there's a space for amateurs to observe solar system objects from the ground, even though we have all this fantastic data from spacecraft. And that space is there because we can do things that the professionals generally can't. We can look at things at different scales. We can look at things with more frequency, particularly objects that professionals observe using telescopes from the ground. Maybe they can only look at them every month or something like that. We can look at them every night. And in fact, with all the amateurs around the world at all the different longitudes around the world, we can essentially keep things under 24/7 observation. So, okay, so this, everyone knows what this is, of course. We've seen some fantastic stuff today about Rosetta. This is the nucleus of 67P Churyumov-Gerasimenko. An amazing object. This is what it looks like from the ground. So the kind of scales that we're seeing here are completely different. So the first thing I'm going to talk about is what kind of resources we have available as amateurs. And of course, in the last 10 to 15 years, the resources that we have available to us have changed dramatically as well. So the technology that we see that goes into sort of big professional telescopes and spacecraft, I mean the amazing focal plane arrays that E2V do, all of the technology there, well we're benefiting from that as well because we have larger and larger imaging sensors, we have better and better camera systems, better and better software, and better telescopes and drive systems as well. So the kind of resources we've got, this is my telescope. It's in my back garden about 2 or 3 miles away from here in Chelmsford. Everyone knows that Chelmsford is a sort of centre of the universe as far as astronomy and solar system work is concerned. We've heard today what goes on here. So this is in my back garden. It's a C11 telescope. I've got a fairly old CCD camera on the back of it. I've also got a wide field system on the side here that I use for wide field imaging. But one of the problems that we've got here and across a lot of the UK is that we suffer from light pollution. So if we're looking at faint objects like comets, for instance, the light pollution does tend to limit what we can do. Although it's still amazing what we can achieve using modern technology, even from light polluted environments. I mean, we're here, so that bright red spot there, but we can still get amazing images. I can regularly, with my telescope system, get down to about magnitude 19, something like that, with a reasonably long stacked exposure. So amateurs still can do amazing things even from urban environments. Every now and again, of course, a comet comes along, and this is just to demonstrate sometimes you get light pollution from the twilight. This is Comet McNaught from, was it January 2007, I think, which was visible in the twilight. So this was taken from Great Barrow, not far away from here. A comet that you could actually see in the twilight, and of course light pollution doesn't affect that at all. But we do have an alternative as well these days, which is to use remote telescopes. And there are now a wide range of telescopes that you can use, either by paying and logging in through the internet and using them, or indeed there are some systems which are free, and you can either use through connections that you might have with schools or other connections you have with astronomy groups. And these telescopes range from relatively small telescopes right up to the kind of 2-meter telescopes that even professionals use. So, you know, the Isaac Newton telescope, which was probably at one point the bee's knees of astronomical telescopes, it's of that kind of size, 2 meters kind of aperture. And there's a wide range of these different systems. I'm sure many people in the audience have used them. They're really easy to use now. This is one which is part of a BAA initiative that if you're a BAA member, you can actually apply for a grant towards the costs of using these remote telescopes if you've got a good project to use them there. This is the Sierra Skies network, and they've got telescopes up to 0.8 meters aperture, so you can use a telescope on Mount Lemmon in the US, which is a 0.8 meter aperture telescope. And of course all these telescopes have really, really nice, expensive, large CCD arrays on the back. Here are a few examples of telescopes from the iTelescope network. This is a network where you pay a monthly fee, and for that monthly fee you get a certain number of points, and you can use those points on the telescopes, and the different telescopes have different prices in terms of points, ranging from sort of fairly low costs for a small refractor here up to fairly eye-wateringly high costs for the big 0.7 meter here. But sometimes it's worth spending the money on these, but clearly you use whichever telescope is appropriate for the object that you want to observe. And the advantage of all these remote telescopes are they're generally in sites with better weather than the UK. They're large telescopes with big expensive CCDs on them, and essentially you just have to pay for the time that you're using them rather than to pay for the whole telescope and have it sitting down the bottom of your garden where it's not being used for 99% of the time. And just as an example, the kind of money that you'd have to spend to get one of these remote telescopes, this is one of the fairly typical telescopes on the iTelescope network. It's a 0.5 meter aperture corrected Dall-Kirkham astrograph. It's got a really nice FLI CCD, big field of view for such a large aperture telescope. It's in a really nice location. It would probably, if you put together the cost of the telescope, the camera and the mount, it would set you back something like $65,000. Now, very few people could really justify spending that kind of money to put a telescope in their garden in Chelmsford, but you can use a telescope like that as if it's yours, just for small parts of the night, by paying a small fee, and you can observe objects, and you can get very high quality data from that telescope. And the nice thing about these things is that generally you can get access to these telescopes very quickly. So if an event occurs, you can just log on and you kind of hopefully get access to the telescope within minutes or hours to do your observation. And of course, right at the high end, some people have access to much larger telescopes. This is the Liverpool telescope on La Palma. There's some access that amateurs can get to these 2 meter class telescopes. There are also the Faulkes telescopes, and if you're involved in some schools groups, you can get access to those. And a really good project within schools is to take up something like a monitoring of a comet or something like that with these really big telescopes. Because in fact, if you go the school's route, you can get access to telescopes which, you know, professionals put a lot of effort in putting huge amounts of kind of proposals in to get access to telescope time on these, whereas the telescope time is kind of given to schools. And far better that you use it for some really interesting scientific project than for taking the sort of 100th image of some deep sky object or even Mars or something like that. Anyway, talking about planets, there are really, I think, 2 very key examples I'd like to give of why amateur observing is still very, very important, even in the current age of spacecraft. And planets is one of the areas. So we've heard a lot about missions to planets. This is Juno. It's arriving at Jupiter later this year. One thing, by the way, that's fairly quick to distinguish a professional image from an amateur image. If the red spot's at the bottom of the planet, it's usually a professional image. That's because professionals put north at the top. If the red spot's at the top, it's usually an amateur image, because for historical reasons, amateurs tend to put south at the top. That's because telescopes invert the image, and so images still seem to kind of conform to that. It's a bit variable, and sometimes, and it's a very irritating thing, and I haven't had time to sort it out in this presentation, is that planets flip up and down depending on which convention people are using. Anyway, so Jupiter's arriving later this year. Sorry, Juno's arriving at Jupiter later this year. And so what amateurs can do now is really quite extraordinary in terms of monitoring planets. Now, you saw some images from Hubble earlier on today. This isn't from Hubble, this is from the nearest equivalent that we've got to Hubble, which is Damiens Peach. Now, one of the really spectacular changes that's taken place with technology over the last 10-15 years or so is the ability to obtain images right at the very limiting resolution of the telescope from the surface of the Earth. And of course the way that's done is you use a camera to take high-speed video of the planet, and anyone who's looked at the planet from the surface of the Earth at a high magnification will know that the planet is boiling and bubbling all the time, and that's called seeing. But if you look at a planet for long enough, and if the weather conditions are right, every now and again the seeing sort of settles down, and for a fleeting moment you get to see an amazing amount of detail on the planet. And those of you who do visual planetary observing will know that you can look through a telescope and you train yourself to look, and then every now and again that fleeting detail comes along and you can sketch that. The electronic way of handling that is you actually take a video at as high a speed as possible, so as many frames per second as you can manage given the brightness of the object you're imaging, and then you go through with software to effectively extract those moments when the seeing is good and throw away those moments when the seeing is bad. And so by doing that, and a lot else besides, you can end up getting images that are, you know, like this one. So this is Jupiter. This is from March last year. A great red spot there. You can see it's an amateur image because it's at the top. But lots and lots of detail here in these belts. And so one of the things that the professionals want when they have a spacecraft in orbit around a planet is that generally that spacecraft has got a quite narrow field of view, and it's quite difficult to target it. And so they can rely on amateurs to actually identify interesting features which they wouldn't otherwise know about. So they might be imaging using Hubble, but the rate at which they can image a planet with Hubble is maybe, well, it's quite limited, so maybe sort of at a frequency of once every few weeks or so, whereas amateurs are really literally these days imaging planets constantly. So it's almost with the distribution of amateurs around the world that they are obtaining high-resolution images of planets at a cadence of hours or so. So you have a very, very continuous coverage. And so amateurs can look for interesting features in the belts, so spots, so you can see some interesting ones here, where things are actually starting to happen in the weather of these planets. And then that can direct the people who are actually managing the spacecraft to go and look at those things, of course in much more detail, but it's the amateurs who are the ones who actually find the stuff in the first place and direct the professionals to look at it. And really there's a lot of this going on in the planetary world just because of the quality of imaging and the number of amateurs who are doing this. And there was a really interesting paper, I think this is the February journal. If anyone's interested, go and have a look at the February journal of the BAA. A very interesting paper on professional amateur cooperation in solar system planetary studies. And when you read that, you just realize how incredibly good the data that amateurs are now getting on planets is, and how much amateurs are actually contributing towards planetary science with this data. The other thing that amateurs are now doing is not just producing these really nice, colourful images of planets, but they're imaging in a wide range of wavelengths. So across the sensitivity range of the cameras that they're using with specialised filters, they're able to image planets at a wide range of different wavelengths. And that's something which tells you a lot more about an object than simply an image in one waveband. So multispectral imaging, which is the posh way of saying imaging in lots of different filter bandwidths, tells you a lot more about the planet. And so these are some really interesting, really nice images. These were taken at peak to midi, I think. Is it peak to midi? Yeah, so with a 1 meter telescope. But again, you know, amateurs have access to these telescopes, showing features in methane band here and other bands, these spots and how they're bright in methane and dark in visible wave bands. And again, all of this information is really useful to the professionals who are running these programs in that it directs them to actually look at objects, and it also gives them a much higher time resolution. So in terms of spatial resolution, they're lower resolution than Hubble, but in terms of time resolution, they're much higher. And in understanding the motion of these objects, the time resolution is really important, because these are weather systems and these things are actually moving in jet streams around the planet. So yeah, this is another Damien image just to show you what kind of quality you can get. This is actually just from last month. So Damien, I can never remember, Dave, is it Barbados? Bermuda, yeah. Barbados. So Damien has actually, Damien, to get his really good images, he actually leaves the UK and he goes off to Barbados with a C14, I think it is, and the latest webcam, so the latest, greatest webcam that is the most sensitive, can take the highest number of frames per second. And he goes to Barbados and he records terabytes of video data and then processes it to produce images like this. And Damien is right at the top of the tree, but there are other amateurs who produce images that are very, very similar quality, very close quality. And then there are other amateurs who maybe don't quite get to the quality that Damien does, but still they produce very high quality planetary images. And all of those planetary images, you know, people can post those planetary images to Facebook and they get lots of likes and whatever, but they can also send them into the BAA and to other organisations where they actually get analysed. And the professionals also set up sites to allow cooperation. So this is a site set up by the Juno science team where observers can upload their images of Jupiter to the site. And then the science team can actually use them, and they're available as essentially a database of science images of Jupiter at a very high time resolution, a very high time cadence, which are available both to professionals and amateurs, and which, when Juno actually gets to Jupiter, will be used as a great resource for planning Juno's operations. And here's just an example of an image that's been uploaded here, and you can go to this website and you can look for images of Jupiter on particular days and at particular times. So another interesting thing that's come out of the fact that imaging is now done using video rather than stills is that at any one time there's probably several amateurs running webcam imaging or high-speed camera imaging of a planet like Jupiter. And this is a really interesting bit of video. If you watch, oops, let's run it again. If you watch over here, this was shot by an Australian guy called Anthony Wesley. You see that there? What that is an impact of an object into Jupiter's atmosphere. Now, we all remember the Shoemaker-Levy comet crash into Jupiter, which was a really spectacular event where a large comet had been gravitationally disrupted and then sort of bombarded Jupiter's atmosphere and left lots of scars in the atmosphere. At the time, I think people said, you know, that was a once in a lifetime, once in however many 100 years thing that happens. And of course, there was no other definite recorded event of an impact on a planet. But because now amateurs are continually video recording these planets at high resolution in order to get their high resolution stills, there have been now, I think, David, you said, is it 5 now confirmed? 5 now confirmed impact events. So this is June 2010, and since 2010 there have been 4 more of these. So they're obviously much more frequent than people initially thought. Because you wouldn't just from sort of one of these say, okay, that was an impact. It might be some electronic noise or whatever, but all of these are confirmed by another amateur somewhere else imaging the planet and seeing the same thing. So I think in this event there was another amateur in the Philippines, Chris Go, who got an image which showed the same event at the same time. So definitely a real event, a real impact. And the same is happening nowadays. And it's got to the point where people have actually developed software where instead of just running your image through Registax or AutoStacker to actually stack the image to get a nice image, the software is also looking for these impact events. And of course, if you've got a spacecraft in orbit around Jupiter that's looking for interesting things, looking at the site of one of these impact events would be a very interesting thing to look at. And so again, the professionals are depending on amateurs to alert them to these impact events. So moving on to another planet, and probably the most beautiful planet in the solar system, this is Saturn, of course. This is last month, again, a lovely Damiens image of Saturn. Just incredible, the kind of resolution. And there's a thing in the South Pole, and this is the South Pole because, of course, it's an amateur image, upside down, don't forget. The thing in the South Pole that was imaged by spacecraft is called the South Polar Hexagon. And you may be able to see it there. It shows up quite nicely. It's a very strange feature that's a kind of hexagonal feature at the South Pole of Saturn. And that's now, amateur imaging is now so good that that is regularly imaged from the ground in just amazing resolutions. So again, professionals are interested in amateur images of Saturn because we've got Cassini going around Saturn at the moment. And again, Anthony Wesley identified back in 2010, I think again, a storm on Saturn, what's called a white spot on Saturn. And this is one of his images at the point that the storm had reached its maximum extent. So this is the telescope he used for that. You can see the storm there. This is 5 years ago, so the quality of imaging has improved dramatically since then. But just to give you an example of what that looked like to Cassini, that's what Cassini got. But the people who run the Cassini mission were alerted to the existence of that white spot by an amateur observing the planet. But I think that's a gorgeous image. You've got the Cassini is almost in the ring plane here. You've got the rings, the shadow of the rings, and this remarkable storm here. And there you go. So Anthony Wesley, Chris Go, and Mark Delacroix got their names on a Nature paper, along with all these very, very worthy people, including Carolyn Porco, who we heard about earlier. So that's what can happen. Amateurs can get into the professional literature as well. And most professionals are pretty good about this. So if you've made some observations which a professional uses when they write a paper, they will generally offer to make you an author of the paper, which is a good thing. And for amateurs to be an author in a Nature paper is pretty impressive stuff. I did like this though. So this goes back a bit to what James was saying earlier on. So you think of amateur images of Saturn, right, as being the kind of stuff that Damiens does. This is a featured amateur image of Saturn. Can anyone spot why that might not have been taken from the Earth? So I think they're kind of stretching amateur image a bit far here. So this is really what James was saying earlier. This is taking Cassini data and processing it. Again, amateurs are doing this really well. So one of the things, and this applies to ground-based imaging as well. Nick Shimanek, who a lot of you know, did some fantastic work for the telescopes on La Palma, where he actually took the raw data that the professionals used for scientific use, and he processed it into fantastic images that is just great for publicity and outreach and all that kind of thing. So again, this facet of what amateurs can do using data that's either generated by professionals on spacecraft or ground-based telescopes or whatever, and producing a kind of, you said sort of artistic, but a thing an image that people can relate to, again, I think is a really important facet of that. So okay, on to my specialist subject, comets. And comets is an area where there's a very big cooperation at the moment between amateurs and professionals. And that's because of this thing, of course. This is Rosetta. And strange, the projector's got green stuff on it. But anyway, that's the nucleus, 67p. That's the spacecraft. And you think, well, okay, why on earth would we want amateur observations of this comet when we can get images of the nucleus of 67p that look like that? Or even that look like that. So that's the image from Philae on the surface. Well, the reason is that you're looking in completely different scales. So this is a fairly wide-angle view. This is the wide-angle camera on board Rosetta from a range of 75 kilometres. About 3 kilometres there, something like this. This is an image taken by Tony Angel in Spain, and it's a completely different scale. So here's the comet, here's the tail you can see going behind the comet, here's the coma, and this is 1.6 million kilometres on the sky. So, you know, the nucleus there is a tiny, tiny, tiny thing in there, you know, a millionth of a pixel or something like that. So what amateurs are doing, or what ground-based observations are doing, is that they're looking at the comet in a completely different scale to the images that the spacecraft are using. And there's again a website that's been set up to facilitate the cooperation between professionals and amateurs here. It's the Rosetta ground-based campaign. There's an amateur part of that. And the amateur part's got a very active Facebook group where amateurs are posting images and information, and the professionals are then kind of commenting, posting some of their observations, posting some of the stuff that comes out of Rosetta, and also feeding back to the amateurs. So it's a really good way of the two groups cooperating. And in fact, there's kind of a blurring of the line between some of the very high-end amateurs who are taking some very spectacular images and the pros in this. And what the amateurs are really doing, again, is trying to kind of look at the comet in this much larger scale. So to assess what the comet looks like at a much larger scale, and to characterize certain features of the comet that you can measure at that scale. So this is a light curve. This is a light curve for the comet, 67p. And all these dots here are estimates of the magnitude or how bright the comet is. Now, if you're a variable star observer, this would be a lamentably bad light curve. I mean, the kind of estimates here go from magnitude 11 to magnitude 15 or something at the same time. So a huge spread. And the main reason for that is the way that some observers are actually reporting magnitude. So unlike a variable star, which is a nice point-like thing where you can actually kind of measure its magnitude very easily, a comet by definition is a big fuzzy thing. And measuring the brightness of a big fuzzy thing is complicated. So most amateurs who do comet work use this fantastic piece of software. It's called Astrometric. It's some software that allows you to take multiple exposures, stack them at an offset which corresponds to the rate that the comet's predicted to move at, and then measure very precisely the position of the comet. And you measure it precisely because the software has actually registered all the stars against a star catalogue, and the catalogue's got very accurate positions in. And then you can actually click on the object and get a very precise position in terms of RA and DEC, but also Astrometrica gives you a magnitude. Now that's all very well for an object like this. This is an asteroid, because asteroids are nice point-like things, and the magnitude means something. For a big fuzzy comet, the magnitude of what's sort of in this central part is not really the magnitude of the comet. And so there are other methods that people use that involve much larger photometric apertures and other methods. And these are some observations made using those methods. You can see the scatter's still large, but it's down to a magnitude or so. And so what you have there is a light curve which essentially shows how bright the comet is as it moves towards its brightest at perihelion and then as it moves away again. And one of the things that the people running the Rosetta mission are interested in is if there's any sudden departure from that light curve, so what's called an outburst. Because comets are very temperamental things, and we all know that it's extremely difficult to predict what a comet will do. And so you can sort of try and predict it by drawing a line through this light curve, but it's possible that for one reason or another the comet might suddenly decide it wants to be brighter or fainter than the light curve, and that's something interesting for the Rossetti team, because they can then look at their data, which is on a much smaller scale, to see if they can actually see stuff near the nucleus that would explain that global change in brightness. So amateurs have been very busy. One of the busiest here is Tony Angel. He takes images. He's got an observatory in southern Spain. He takes images regularly of the comet. And the good thing about them is they're all taken with the same equipment. They're all processed in the same way, so you can actually compare one set of images to the next. Although I say Tony Angel's got good conditions in Spain, this was taken from the amazingly dark mountaintop skies of Leon Sea. And it shows again that if you have the right technique, you can do this work. So Peter, who lives, what is it, about half a mile from Southend Airport in Leon Sea, just has got very good technique, very good flat fielding, and can get really high quality images from his site. So it's a good reason to say that just because you live somewhere that's urban, suburban, light polluted, you can still do really, really good work. And Peter posts a lot of images to this group, and I'll come to it in a minute. Part of that means that he's got sort of a good sampling of images that's helped to sort out some queries that have happened recently. This is an image I took actually with one of the remote telescopes. This is taken with the 0.8 meter telescope on Mount Lemmon. And again showing the sort of technique of measuring the magnitude. So you're not measuring the magnitude or the brightness of this very sort of inner bit, you're measuring the brightness of this whole coma that's visible here. Another Tony Angel image. And this is a fantastic image, again showing the difference between the very, very tiny scales that we're looking at with the spacecraft and the very large scales you can look at with instruments on the ground. This is Slough, which is one of these online observatories. These are taken with a telescope on Mount Teide in Tenerife, I think, but show a very, very long tail here. It's a bit difficult to see on this screen, but the tail actually goes off the end of the image here. So again, just showing how amateur observers can use sort of semi-professional telescopes on mountaintops through the internet, but processed with software that's been written by amateurs, because there are lots of very clever amateurs out there writing really clever software to produce really good data, which can then be used by professionals to give them a kind of wide field view of what these objects are doing. So again, here's an example of measuring the brightness of the comet. Yes, outbursts. So this is just a sort of quick recent bit of information about 67P. This isn't 67P, this is a comet called 17P Holmes. And it's the most extreme example of a comet outburst that we know of. This comet was at about 15th or 16th magnitude, right at the limit of a big telescope, and in less than a day it brightened up to be so bright that you could actually see it from the middle of Piccadilly in London. This is actually after a BAA meeting. We're here observing the comet in the middle of Piccadilly. Now this is an extreme example of a comet outburst, but 67P has very small hiccups or outbursts when suddenly the dust production or gas production from the nucleus increases and has an effect on the comet. And one of these happened recently in February. It was detected by Rossetti on the 19th of February, and there was a call for images that were taken from the ground on that date. And there were very few because of weather all over the place, but there you go. We've got one from Leon Sea, from Peter here, that was taken at just the time that the professionals needed. So a really good example again of the fact that as amateurs working together with the fact there are so many of us at so many different places, that we get a far better coverage in terms of time than the pros could ever get. And that's our real kind of weapon. It's that very, very fine time resolution that we can get on things. Again, showing, Leon Sea is a pretty good site for astronomy. This is the comet as it is a few days ago. It's fading now, it's moving away from the sun, but it's still got quite a nice tail. So I think comets definitely is an area where we can cooperate professionals. And this is a great quote. This was posted recently. from Alan Fitzsimmons, Colin Snodgrass and Garrett Jones. The rest of the pro team say thanks for all the great images you're continuing to obtain. As you all know, large telescopes have nowhere near the time coverage that amateur pro-am can, and it's been fantastic to see the amount of data that people are collecting. So again, a really, really good example of where amateurs can support space missions with relatively simple equipment from the ground. And also a really good example of the feedback from professionals back to the amateur community, showing them that their data is useful. So so that's planets and comets. There's just one sort of slightly off the wall thing I'd like to go through is the sort of last segment of this talk, and it relates actually to the spacecraft themselves. Now you think, you know, when they launch spacecraft, they have huge resources to track the spacecraft, to know where it is, and to measure it. But that's not always the case. And this is a particular example of Gaia. So Gaia, we've already heard about, is an astrometry mission. It has this huge focal plane array that was made here in Chelmsford. It's gone to the L2 point, so the point between the Earth, away from the Earth, sort of in line with the Sun, about 1.5 million kilometers away. But one of the things about Gaia it needs in order to do its mission is it needs to know, or the ground needs to know very accurately where it is in space. So here it is. This is the Gaia spacecraft, and it needs to know. They need to know very, very accurately where it is in space, and they also need to know very, very accurately what its velocity is. As Mark said this morning, I think it was Mark said this morning that, you know, the gravity of Jupiter can deflect the light enough that it can be detected in the Gaia data. Well, just the motion of the spacecraft and its position can also do the same, and the kind of requirements they have on motion and position are very, very tight, sort of millimeters per second in velocity, and I think 100 and something meters in position. And so before they launched the spacecraft, they knew that it was unlikely that they would be able to get that kind of accuracy using just normal radio tracking. And so there was this thing called the Ground-Based Observational Optical Network. And the plan was to use fairly small optical telescopes around the world to actually image Gaia at the L2 point, do very accurate astrometry on it in order to localize its position very accurately. And that was absolutely essential to Gaia doing its mission. If they couldn't do that, then, you know, Gaia, even if Gaia worked perfectly, they couldn't do its mission because they wouldn't know where it was. Now, one of the problems is that they had to estimate how bright this thing was going to be at L2. Now, Gaia has got this huge sunshade. Now, the sunshade in normal operation is angled at about 42 degrees to the sun angle. So essentially, if you imagine looking from Earth, you're looking at the back of a sunshade, which is looking then reflected off somewhere into deep space somewhere. So to estimate the brightness of this thing was quite difficult. You had to kind of have an estimate of how rough the sunshade would be to know how much light would be scattered back to the Earth, back to Earth telescopes. But they thought it would maybe be about magnitude 18. From previous missions, they thought it would be about magnitude 18 at L2. But there was a call for amateurs to actually image the spacecraft whilst it was travelling out from the Earth to L2 to actually measure the brightness of the spacecraft so that they could actually they could update their estimate. And so I did this along with others, and initially the spacecraft was really bright. So this was only a day or two after launch. It was about 10th magnitude, moving quite fast. It then dropped to about 13th or 14th magnitude by the time it got to about 500,000 kilometers out. And then all of a sudden, it dropped from 14th to 18th magnitude overnight. And the reason it had done that is up to the point, so initially at launch, the solar aspect angle of the shield was 0. So it was effectively reflecting sun directly back to the Earth. They then changed the solar aspect angle to 42 degrees. And the brightness dropped like a stone, and it dropped far more than they were expecting. Primarily, I think, because I think it was Astrium at the time who'd made the spacecraft. Their thermal blankets was much smoother than they expected, and so effectively the thing was acting as a mirror, and you're just looking at dark space. And so the observations by amateurs, including my observations from Chelmsford, were the first indication that they had a significant problem. If you extrapolate the magnitude here at 500,000 kilometres to L2, the thing was going to be about magnitude 20 to 21 L2 rather than magnitude 18. And that meant rather than using sort of 20, 30 centimetre telescopes, they would need 2 metre type telescopes to get the accuracy that they needed. So I think that's now what's done. They actually have time on telescopes around the world of that class, the Liverpool telescope and others. But it was the amateur images that were taken on the way out to L2 which were the first indication that they had this problem and they had to do some replanning. So again, this is another example where amateurs using very simple equipment, I mean this was the telescope in my garden at Chelmsford, was providing absolutely vital information to the space mission. And this is the final view I had of Gaia. They did an interesting experiment at L2. So it got to L2 and the heat shield was at its 42-degree aspect angle, and it was about magnitude 21, which was below my detection limit. But they decided that they were going to do a few experiments where they'd actually change the attitude of the spacecraft to bring the heat shield back, the sun shield back to 0 degrees and then back out to 42 degrees. And this is an image I took, I think it was, in March 2014. This was when it was L2, so the spacecraft's 1.5 million kilometres away here, and it went from magnitude 20 odd to magnitude 15 because of this solar aspect angle change, and then as they went back to 42 degrees again it faded away. So I think what they ended up doing is there was a slight compromise in the solar aspect angle, in that they reduced the solar aspect angle a bit to make the spacecraft a bit brighter so that it could be tracked sufficiently accurately with the 2-metre telescopes. So I hope what I've done is given you some good examples of why amateurs can still make a really significant contribution in these days of amazing space missions. And you can do it even if you haven't got telescopes, because you can use remote telescope sites as well. I'd be happy if I think probably haven't got time for questions now, but I'll be around afterwards if anyone's got any particular questions about how to do this and which groups to get involved with in order to interact with professionals. But I think there are some very good examples there, and for me in particular, knowing that what you're doing is actually contributing to professional science just makes astronomy a little bit more interesting. So thank you very much.